This is Graham Gordon talking about cycle type factorizations in GLNFQ. Take it away, Graham.
Thanks again, Sarah. Okay, so here we go. Cycle type factorizations in GLNFQ. I thought I'd start with some quotes that I thought of when I was looking back at my time in grad school. Take them or leave them. Some serious, some funny. In particular, I think my rephrasing of that last one would be, if I had 5 years to spend as I like, I should walk at my leisure towards some results on enumerating factorizations in GLNFQ. Okay, let's move on. So I'll introduce some concepts and then tell you about the factorization results that I found, and then take you behind the scenes a bit and tell you how they work. And then we'll talk about some polynomiality results, kind of branching off of the enumerative factorization results, and then look at some open problems, and that'll be the talk. So here's the intro. I first want to start thinking about real classical factorization enumeration question in the symmetric group S4. I'll denote that with this fractor font S. So let's think about this standard 4 cycle. 1 maps to 2, maps to 3, maps to 4, and back to 1 cyclically. And we can write that as a product of transpositions. So we could write it as the transposition 3, 4 times the transposition 2, 3 times the transposition 1, 2. And I'm thinking about these as functions composing, so kind of like a right to left multiplication. And there are multiple ways to do this. I could also do 1, 2, times 1, 3 times 1, 4 over there. And one question you could ask is, how many ways are there to do that? And here's an answer, a theorem that comes from the work of Horowitz, also comes from the work of Danish. So the number of n-1 tuples of transpositions in the symmetric group, whose product is this standard n cycle, 1 maps to 2, maps to 3, up to n and back to 1, equals n to the n-2. Now, I highlighted Danish's name. This is not supposed to be calling him out, but I think that the proof there is not actually right. But luckily, the result is still true. Then I also highlighted this n to the n-2 number, because you might recognize that as the number of labeled trees on n vertices. So Danish's proof basically does an overcounting argument, and the way it works is you can label the edges in all possible ways, and you can label the vertices in all these ways, so that each edge corresponds to a transposition. So this edge, because it goes from 3 to 4, corresponds to this transposition 3, 4, then switches 3 and 4, and likewise this 2, 3 edge corresponds to this transposition 2, 3, etc. And if you look at all possible, if you look at all the trees on n-labeled vertices and all the labelings of all the orderings of the edges, that corresponds to all possible factorizations of arbitrary n cycles. And then you can divide out by the number of n cycles, and you've gotten this n to the n-2 number coming from the tree structure. Yeah, so that's kind of a classical result that says, here's the factorization enumeration question in the symmetric group, and here's an answer in terms of graph theory in this case. So now I want to generalize some of these notions a little bit, introduce some notation. So I'm going to let this C mu symbol denote the conjugacy class of permutations with cycle type mu. And I'm going to use chi with an superscript lambda and subscript mu to denote the Sn irreducible character chi lambda evaluated at C mu. So just to use the notation, the transpositions like we saw from the previous page that just have a single 2 cycle and then n-2 fixed points are as denoted by this. It's, C sub 2, 1 to the n-2, and then, oops, all right, that's fine, there we go. The degree of a character is just its value at the identity. So that's using some of the notation there, and now let's write down what for me is the main inspiration for my project here. So now if I've got a positive integer k and a partition mu of a positive integer n, I'm going to use gk mu to denote it's another factorization enumeration, but instead of factoring an n cycle into a product of other things, I'm actually going to count how many ways can I take k n cycles and multiply them together to get something with cycle type mu. So it kind of flips the original picture in reverse, factoring things in n cycles rather than factoring n cycles into other things. So for instance, let's just look at an example here. If I take that standard the standard 4 cycle and multiply it by itself, I get two cycles. So this over here is not written in a cycle decomposition. It's just a product of two different permutations. But this here is written in the cycle decomposition. So it's two cycles. So this factorization here corresponds to something counted by, or it is counted by this G2 of 2 number. So I'm taking 2 n cycles and I'm getting something of cycle type 2. So the theorem coming from Stanley in like 1981, I think, gives a formula for this. And the way Stanley phrased it was, fix an arbitrary permutation of cycle type mu, and then factor that into n cycles. And that corresponds to just dividing this gk mu number by the size of the c mu conjugacy class. And so Stanley gave this really quite simple formula for it. The coefficient out front of the sum is some familiar numbers, factorials, and then it's a sum over just n terms of there's a sign here, a symmetric group character, and a binomial coefficient to some power in the denominator. And I highlighted that symmetric group character because it's indexed by a hook shape, that n minus r, 1 to the r is a hook. And the hook characters have an explicit formula. It's a little bit long, I didn't want to squeeze it into this slide, but there's an explicit character, an explicit formula for them in terms of binomial coefficients that you can write down that makes this formula totally explicit and very easy to compute computationally. Very nice formula. It's certainly quicker than writing down a bunch of n cycles and multiplying them. Cool. And my main goal is to find basically an analog of this theorem for the finite general linear groups, GL and FQ. I wanted to point out for any potential topology fans in the audience that this has a connection to Hurwitz theory. And yes, it's the same Hurwitz from one of the earlier slides. So the middle of this slide in purple there is one of those numbers from the previous page. So that's counting how many ways are there to write down 3 n cycles, multiply them together in that order, and get the identity. And it turns out if you divide that by n factorial, then on the right-hand side, that formula from Stanley allows you to evaluate it explicitly. But on the left-hand side, you get a Hurwitz number. And that's coming from Hurwitz theory. So that factorization in the symmetric group, which is in the middle, corresponds to enumerating branch coverings of Riemann surfaces on the left. So this Hurwitz number, for instance, you have a degree 3n, a genus 3n minus 1 curve mapping with a degree n covering map to a Riemann sphere, and you have 3 branch points with that are totally ramified, and that's all the ramification. So it's this, and that enumeration is up to isomorphism and automorphism. So technically, you could get rational numbers as counts, which is a little bit weird, but that's how that works. And if you want to check out more on this topic, there's a cool book that I recommend. This first course in Hurwitz theory by Renzo Cavalieri and Eric Miles. Okay, but that's just kind of added flair, a place that these factorization and enumeration questions show up in other areas of math. Okay, so in order to segue into GL and FQ, we need to think about a couple of things, like what's an analog of an n cycle, what's an analog of cycle type, how could we define an analogous factorization enumeration? So let's think about an element in GL and FQ and call it a Singer cycle, which has come up more recently in the literature than the 80s. And this has been thought in the last few years of as an analog of the n cycle. And it's one way to define a Singer cycle is to just check that it has an eigenvalue with multiplicative order q to the n minus 1. And one suggestion, I'll talk later about why I find this a compelling analog of an n cycle. One reason why you might find it a compelling analog is if you write this q to the n minus 1, if you factor it into q minus 1 times the q analog of n, then this suggests that if you quotient out by scalars, so quotient, like basically divide by this q minus 1, then the resulting element has order, the q analog of n, kind of analogous to the fact that the n cycles just have order n. But yeah, like I said, I'll talk more later about why I find this a compelling analog of n cycles. So here's the theorem from Lewis, Reiner, and Stanton in the last few years. That says, if you look at the number of ordered n tuples of reflections in GLNFQ whose product is a fixed arbitrary Singer cycle, then that count is q to the n minus 1 to the n minus 1. So what's going on here? This is kind of an analogous result to the transposition factorizations of the n cycle from the first page, and it appears in a paper called Reflection Factorizations of the Singer cycle, and so basically, you can think about reflections in GLNFQ as analogous to the transpositions in the symmetric group. In particular, they are the reflections viewing Sn as a reflection group. And it turns out that you need n reflections to get a Singer cycle in GLNFQ, and that just comes from looking at the dimension of the fixed space. And yeah, you get a really concise answer, kind of like in the symmetric group, you get this n to the n minus 2 number. Here you get q to the n minus 1 to the n minus 1. It's maybe not clearly a q analog of n to the n minus 2, but it has this kind of similar flavor, and it's still very concise. Cool.
And there's a question in the chat asking which matrices are the reflections?
Oh, the reflections, exactly. It's just that the fixed space has codimension 1. So geometrically a reflection, yeah. They could have varying determinants, but yeah, just check the fixed space has dimension n minus 1. Cool, so.
And it also has to be an involution, right?
Oh, that's the weird thing. Not in GLNFQ. Yeah, these reflections are not necessarily involutions.
Oh, okay.
Yeah, that's pretty weird. Yeah, good question. Yeah.
Thank you.
Yeah, no problem. Here's another result. This actually results coming from Joel Lewis and Alejandro Morales in the paper that really inspired me to approach this project. It's less concise to state, but I still think it's a cool result. So if you fix a Singer cycle, and I highlighted that because it's true for a more general class of elements we'll talk about later, but still, at least it's true for Singer cycles. And you can now instead count factorizations of the Singer cycle into elements where instead of requiring them all to be reflections, you can just specify what you want the fixed space dimension to be for each of them. And I just wrote it down for the case of 2 factors, so that would fit on the slide. Although I guess the more general case is not too difficult to write down. But yeah, I think it's an awesome result because, well, on the left-hand side, we have this A sub Rs of Q enumeration. And on the right-hand side, even though it's maybe kind of lengthy, it's still all just explicitly defined terms. So it gives you a way to compute these numbers from the perspective of a generating function. So yeah, definitely wanted to point this out. This is kind of the first paper I read about this and got excited thinking about it. So yeah, now I want to segue into talking about my own factorization results. And let's start with thinking about the kind of analogs between the symmetric group and GLNFQ that I've seen so far. So Sn acts on the set 1 through n by permuting the elements around, and GLNFQ acts linearly on this n-dimensional FQ vector space. The subsets over in the Sn land correspond to subspaces in GLNFQ, and correspondingly, the cardinality of a subset, you can think of its Q analog as the dimension of a subspace over in GLNFQ. And so recently people have thought, yeah, Singer cycles seem like a reasonable Q analog of an N cycle. And I'll talk a little bit more about a slightly more general class that has also come up in recent work. And what about cycle type overall? What's the analog for cycle type over in the GLNFQ world? And that's the question that I want to address next, so that we can then define an analogous notion of that factorization question of factoring things in the products of n cycles. So let's look at a really concrete example. Here's a matrix in GL6F3, and I've written it not quite in rational canonical form, but close. So this first 3 by 3 block, if you think back to linear algebra, that acts on the first 3 basis vectors and stabilizes the span of them. Over here, we've got an eigenvalue of 1. And this middle block here, it's a 2 by 2 block, so it definitely corresponds to a 2-dimensional subspace that it stabilizes, but it is a unipotent matrix and it has an eigenvector in that subspace. So we can write down these 3 subspaces that whose direct sum is the whole 6-dimensional F3 vector space. And we can start to write down the cycle type, what we think the cycle type of G should be. And because this 3 by 3 block in the top left has an irreducible characteristic polynomial that actually corresponds to there not being any other subspaces in that 3-dimensional subspace that are also stabilized by G. And this is the same as like what happens in the symmetric group. When the symmetric group has a 3 cycle, it acts on a set of 3 elements, and it doesn't stabilize any subsets, any proper non-trivial subsets. So I'm definitely thinking if I'm going to write down a reasonable cycle type for this matrix, that 3 should be in there, and 1 should be in there because I've got this 1-dimensional subspace over here stabilized. But the middle is kind of unsatisfactory to me because I do have an eigenvector, so I want there to be a cycle of length 1 in there, but there's not it's not like a complementary eigenvector. But I'm going to accept the fact that there is one eigenvector, and I'll be forced to write down that the cycle type is 3, 1, 1, 1. That's a partition of 6. And I'm going to call that the cycle type of this matrix G. Now, here's a quote from Stong later in the 80s, who suggests that the analog of cycle is basically a polynomial of whose degree is the length of the cycle. Cycle of length m, polynomial of degree m, dividing the characteristic polynomial. So we can just take that. Let's just take that as the definition of cycle type. And like I said, this was considered in the 80s, but I haven't yet seen someone write down, this is the definition of cycle type for GLNFQ. Let's enumerate factorizations. So I'm going to call this the definition of cycle type. And so basically, given a matrix, write down its characteristic polynomial, factor it into irreducibles, and just record their degrees in weakly decreasing order. It gives you a partition of n, and let's call that the cycle type.
There's another question in the chat.
Oh yeah, what's up?
Josh Thompson asks, companion matrix has no non-trivial invariant subspaces regardless of if its characteristic polynomial is irreducible, right?
No, not totally true. In fact, we just saw an example of that. Like this unipotent 2 by 2 unipotent block has a non-trivial as long as I heard you correctly, that unipotent block has an eigenvector.
But it's not a companion matrix.
Oh, you could write it as a companion matrix. I just didn't write it in like the companion matrix would have a 1 in the lower left-hand corner. Like the companion matrix could be the companion matrix for a reducible polynomial.
Yeah, you could just stick the coefficients in the final column.
Yep, exactly. Yeah.
Huh. I just thought that there were no oh, okay.
I mean, if you want to write down a rational canonical form in terms of just companion matrices on the diagonal, then you need to write down some companion matrices of reducible polynomials.
Yes.
And those will have proper non-trivial invariant subspaces.
Huh.
Yep.
Okay.
It is also true that if you start with the first basis vector and repeatedly apply to companion matrix, you will span.
Yes.
But it is also true that there are some invariant subspaces. Yeah.
That must be the confusion then. Sure.
Yeah. Cool. Yeah. No. Good question. It's a little bit weird geometrically, but we should come a bit later to a result that will help us see even more clearly what's going on in relation with cycles.
Also, Alexander Wu asks whether irreducible means irreducible over FQ.
Oh, exactly, yes. Irreducible over the ground field. Yeah, good question. Precisely, over FQ. Cool, so here's some notation. Nothing deep here, I just want to call this set T sub mu of Q, all the matrices with cycle type mu. And I'm calling it T rather than C because it lumps together a bunch of conjugacy classes. So I don't want to call it C sub mu of Q and risk confusing it with conjugacy. So T for type. Okay, and my philosophy is that that's just a Q analog of the permutations of cycle type mu. Okay, now let's look at another example. And let's try to resolve that issue that we had where we had to kind of accept that there is a one cycle, even though there wasn't another one cycle in that coming from that 2x2 unipotent block. So this is another example in GL6F3. These three are the companion matrices for three distinct irreducible polynomials. So I've replaced that unipotent block with an irreducible polynomials companion matrix, and that guarantees that there isn't an eigenvalue in there. So these subspaces U and V and W of dimensions 3, 2, and 1 respectively have the property that none of their proper non-trivial subspaces are stabilized by G. So I'm much more confident in believing that those geometrically look like a 3-cycle, a 2-cycle, and a 1-cycle. And also we can just use the definition from Richard Stong and say, okay, 3, 2, and 1 are the degrees of the irreducible factors of the characteristic polynomial. That means the cycle type should be 3, 2, 1. And like I was saying, those are the dimensions of these subspaces that these blocks correspond to. Now this matrix has another really special property, which Stong talks about in the conclusion of one of his papers, but also there's some other people to check out, Kung and Lair and Fullman, for their comments on this phenomenon. Yeah, I guess the short version of this is that the regular semi-simple variety is dense or whatever. But at least enumeratively, for GL and FQ, as Q gets large, there's an arbitrarily large proportion of elements that have no repeated factors in their characteristic polynomial. So it's, yeah, enumeratively, at least as Q gets big, this is kind of a weak condition that we've specified that these polynomials are distinct. But I want to try to convince you that geometrically and algebraically, it's a really useful condition. Now, if Q is small, there's a chance that these elements don't even exist at all in GL and Q. But here is the theorem. Now, this goes back even further. This is like in the 60s, I think. If you look at the lattice of stable subspaces of a matrix in GL and FQ, then you get that it's a Boolean lattice if and only if there's no repeated factors in its characteristic polynomial. So let's look at, for instance, what if we take that matrix we just had, its cycle type was 3, 2, 1. There are no repeated factors in the characteristic polynomial. And if we write down the lattice of stable subspaces, then those same subspaces, U, V, and W, are the atoms in this Boolean lattice. I guess that should be F3 to the 6 in that example. Here Q equals 3, but no worries. And for instance, in the situation when we had that unipotent factor, that would correspond to having some kind of diagonal. Basically, if there are repeated factors, you'll get these diagonal subspaces that break down the fact that they cause the poset not to be Boolean anymore. But this is a much more clear analogy with a symmetric group, in that if you look at the lattice of stable subsets of a permutation with cycle type mu, then it decomposes, or you get a Boolean lattice, and you can see that, like, you know, the dimension of U is 3, the cardinality of this corresponding set is 3, etc. Dimension of V is 2, and so on. So from the perspective of invariant subspaces or invariant subsets, and as long as we're talking about these matrices with no repeated factors in the characteristic polynomial, this to me is a clear geometric reason why we should think about these as kind of Q analogs of, or why we should think about this definition of cycle type as a Q analog of the corresponding definition in the symmetric group. Okay, where are we at here? All right, so I'm just going to give a name to this. This is called regular semi-simple, this property of having no irreducible factors in the characteristic polynomial. Jason Fullman gave a nice combinatorial description, which is what I use to think about these in my paper. And because this condition corresponds to each polynomial showing up at most once in the characteristic polynomial, I'm going to use the superscript of a box. Oops. Oh, that's hilarious. It's not a checkbox. Okay. That is the Young diagram for the unique partition of 1. And so basically that just corresponds, that just means I'm thinking about polynomials showing up at most ones. And like I said, as Q gets large, this is an arbitrarily large proportion of GLNFQ. So I'm still going to think about these as a Q analog of C mu. And in fact, geometrically, I find them a much more believable analog. I kind of like the checkboxes though. Maybe I'll check both of them. Okay. Now let's note in the case that mu is the one-part partition in, that's what I want to think of as the analog of the n cycles. And this class is called the regular elliptic elements. And that contains the Singer cycles like I talked about earlier. So now I've come back around to showing why, from my perspective, I see the Singer cycles as believable analogs of n cycles. And so now I can define the Q analog of those factorization enumerations that I said were my main, was my main inspiration. So now I've just tried to swap out the n cycles of the symmetric group with the n cycles of GLN of Q, and the cycle type mu permutations with cycle type mu matrices. So this GK mu of Q number is just the number of K tuples of regular elliptic elements whose product has a given cycle type. And I also have a version for regular semi-simple elements if I want to consider those. And my philosophy is that both of these are Q analogs of the original GK mu function that Stanley found that formula for. Okay. I gotta say, I did not know that these checkboxes were going to be checkboxes, but I like that quite a bit. So here's a picture of what's going on, a little bird's eye view. The whole screen is GLNFQ. This largest bubble in the Venn diagram is regular, I guess it's not really a Venn diagram, but the largest bubble is the regular semi-simple elements. So as Q gets big, that's most of the screen. Zooming in a little bit, we have the regular elliptic elements that we just talked about, containing the Singer cycles. And then off to the side somewhere, if mu is not that one-part partition in, then we can think about cycle type mu elements. And we can also think about restricting that to cycle type mu elements that are also regular semi-simple. So this is just, this cycle type mu regular semi-simple portion is just inside. And this cycle type mu in general is the entire ellipse there. So my question is, how many ways can I multiply things over here and get things over here? Okay. So here is the main result. All right. So if you look at this, the particular case, which is what I've highlighted here, when that partition mu has exactly one part equal to 1, and every other part is bigger than 1, then here's the formula that comes up. And I'm also looking at just the regular semi-simple case. Turns out the regular semi-simple elements are just really nice to work with, and I'll try to motivate that more in a bit. So the factor out front is kind of just familiar enumerative things. It's the number of K tuples of regular elliptic elements times the size of the cycle type mu set divided by the size of GLN of Q. But then there's something that I hope looks really familiar. It's a sum of R terms of a sign times a symmetric group character divided by Q analog of a binomial coefficient to some power. So if you compare that to this following rephrasing of Stanley's result, then you can see, I hope you can see much clearer that this is, yeah, basically a Q analog. And I'll talk on the next slide about maybe more precisely how it's a Q analog of the symmetric group result. But at least the formulas look quite analogous. I've just swapped out the corresponding sets with what I see as their analogs. And the numerator over here in the sum is exactly the same, actually. It's still in terms of signs and symmetric group characters. And the denominator is an honest Q goes to 1 analog of the denominator of the symmetric group result. Yeah, and this is, again, for all, just the cases in which there's exactly one part of mu equal to 1, and just for the regular semi-simple case.
And there's a comment in the chat. Gil says, this looks very beautiful. Do you have some Q large convergence here as well?
Yes. Oh, yes, exactly. Next slide. You're one step ahead of me. So first of all, I'll talk about Q goes to 1, then I'll talk about Q goes to infinity, yeah. So under these previous hypotheses, so just in the cases that I just have that formula for, but I'm glad you think the formula is beautiful, so do I. If you just divide by all of those factors out front, unfortunately those factors themselves don't behave nicely in the Q goes to 1 limit because of a bunch of Q minus 1s running around. But if you divide those over, then you do get a Q goes to 1 analogy, basically just because that denominator was a Q analog. But if we look carefully at what's going on here, the numerator here is the probability that a random K tuple of regular elliptic elements has product with cycle type mu. And the denominator is just the probability that a random element in GLMQ has cycle type mu. So you can kind of think about this fraction as a ratio of 2 probabilities. And you can kind of think about them as like different ways to try to get random elements in GLMQ. The numerator says multiply a bunch of random regular elliptic elements together. And the denominator says pick an element at random, right? So for some reason, these ratios of probabilities are Q analogs of each other, at least in the situations that I have that the main result holds for. And here's a theorem. This is the Q goes to infinity limit that you're just asking about. And this is true for any partition mu. So if I look at that same ratio of probabilities, and I take any partition mu, it doesn't have to just have m1 of mu equals to 1, and I take the Q goes to infinity limit, this ratio actually equals 1. And so what that means is, if you look at multiplying a bunch of random regular elliptic elements together and ask what's the probability I get cycle type mu, it's the same as just taking a random element in the first place and asking, did I get cycle type mu? And then, yeah, so it kind of seems like multiplying a bunch of random regular elliptic elements together just kind of distributes you uniformly throughout GL and FQ. And the same holds without the box. I can't check that. Oh, I can check that one. Great. The same holds without the box. And the reason that is just as Q goes to infinity, the distinction between regular, semi-simple, and not is it goes to 0. Cool. So yeah, that hopefully gets at what you were asking about in the chat there. And one other thing I might point out, this denominator, I mean, both the numerator and the denominator converge, and they converge to 1 over the size of the centralizer of a cycle type mu permutation. So basically that says that cycle type in GL and FQ and cycle type in the symmetric group partition the groups in enumeratively similar ways. So kind of interesting connection with the symmetric group there.
There's another comment
or
question. Jared Alper asks, is the formula in the main theorem wrong if m sub 1 of mu is not equal to 1?
Yep, that is not the right formula. And there's, I'll show you in a sec an example of where that really a very different formula has to be true. But yeah, great question. It's because you can still, and you can evaluate it for all kinds of things. You can evaluate it for Q not a prime power because these coefficients out front have explicit formulas. It's a weirdly easy thing to plug things into. Yeah, but I will show you in a bit where this goes wrong. Here's a really simple corollary. I just like this because it highlights another subtle distinction between GLNFQ and the symmetric group. If you let mu be that partition n minus 1, 1, it satisfies the hypotheses of the main theorem, and we don't need to specify regular semi-simple anymore because n minus 1 and 1 are different, so you have to have different factors. And that sum collapses just using the symmetric group's character theory to having just 2 terms, and the symmetric group result looks similar. But the weird distinction I wanted to point out is that in the symmetric group, this sum of 1 and minus 1 to some power is either 0 or 2, and the zeros are coming from a parity condition. Basically, you just can't have certain permutations multiplying to each other just based on their evenness or oddness. But in GLNFQ, because Q is a prime power here in the denominator, that's never equal to 0. So it highlights that's a pretty significant difference, I think. I mean, of course, there's lots of differences between the symmetric group and GLNFQ, but that's kind of a particularly interesting one. Okay, now here's where that niceness of that formula really goes completely haywire. So if you look at factorizations where you're multiplying regular elliptic elements and you want to end up with something that's still regular elliptic, that's the same as plugging in mu equals this one partition n. I've got a formula for it, and I'll show it to you. You might not even call it a closed formula because it involves a bunch of nested sums over the divisors of n. But one thing that suggests is if n is prime, then the formula should simplify quite a bit, and that will happen later in the talk. And I also am not quite sure how to compare it to the corresponding symmetric group result. It really is just so much messier than that first result that I don't know how to compare this yet. So, oh yeah, before I show you that. So you know that I'm not bluffing. Here's a way to write down that formula. These are 4 functions. I think I'm sort of behind time, so I'm not going to spend too much time talking about this. These are 4 functions in terms of Q that you can write down if you want, and you can use them to write down an expression for GKN of Q. And I just divided it by that capital P function so that it all fits on one line. The main hiccup here in terms of believing that this is a nice formula is the fact that this denominator is computed in Z, not Z adjoin Q. So that is not even that's not a polynomial or a rational function of Q. And that kind of throws everything for a loop. Basically, that's a reason why that original formula can't work for some other values of mu. Anyway, just wanted to put that there so that it's out there in case you want to look at it sometime. Maybe you don't. Okay, and so of course some of the missing cases that I haven't addressed. The main thing is that if the multiplicity of 1 and mu is not 1, I don't know in general what's happening there. I'll try to motivate in a bit why having that multiplicity of 1 equals to 1 made things so nice. But at least some progress that I stuck in my thesis at some point. If you put some assumptions, like if you make sure Q is even, if you make sure N is odd, and you look at either this N minus 2, 2 partition or this 2, 1 to the N minus 2 partition, then that same formula does work. This is the same formula from the main result. But if you relax the evenness of Q or the oddness of N, it's a lot messier than that. Yep. So just there's a little bit of progress. It's showing me though that the techniques I'm using aren't really going to allow me to get much further than that main result. Okay, I think that's all I was going to say about the results that I proved. Well, there's some more results later, but those are the main enumerative factorization results. So I was going to take you behind the scenes a bit. And also, I'm glad that all the questions have been kind of coming in naturally, and thanks to Rowan for interrupting me. So keep them coming. Here is the main technique that goes into this, which JR showed me this formula probably my first year of grad school. And I never forgot it. So if you have a finite group G, and you specify some unions of conjugacy classes, A1 through AK, and some element, little g, you can count the factorizations of G into products of elements such that each factor comes from one of the specified conjugacy class unions using the character theory of G. So if you know the irreducible characters, I'll try to highlight just the subscript there. If you know the irreducible characters of G, then you can take the sum over their degrees to some powers of some character values. And one cool thing about this is that it kind of converts, over here you've got products of elements in the group, and over here you just have products of complex numbers in the complex plane. So in some sense it bridges, it just kind of eliminates the need to actually multiply group elements, and you can still enumerate factorizations. So in some sense, this is the answer to the question. How do you enumerate factorizations? Here you go. And for the symmetric group, we have the Murnaghan-Nakayama rule, which is this very nice combinatorial formula for the characters. You have this signed sum over border strip tableau of shape lambda and type mu. It's so concrete that there's an example on the Wikipedia page that walks you through how to do it. And yeah, I highly recommend, if you're curious about the Murnaghan-Nakayama rule, to go work through an example there. Here's what I was able to come up with.
There's a comment in the chat as well. Alejandro Morales Barrero, sorry, pronunciation, asks, for the previous result for n-2, 2, since you have a result for limits of q going to infinity, then q equals large odd looks very similar to q even.
Oh, interesting. So probably what that means is, so when q is odd or n is even in the n-2, 2 case, I kind of phrase the result as this factor out front just has to pick up plus some error term, plus some epsilon. And probably what that means then is that as q gets large, that error term goes to 0. Yeah, that's a really good point. Yeah, thanks for pointing that out. I'll have to take another look at that. Let me write that down. Error goes to 0 as q goes to infinity, question mark. Probably that's what happens. And I think that the similar thing should probably happen for these kind of look like transpositions from the perspective of cycle type here. And so probably something similar happens there. Yeah, thanks. Cool. So, right. So here's what I was able to come up with for the characters of GLNFQ. It's not as nice as the Murnaghan-Nakayama rule, in my opinion. It's just, there's more data in GLNFQ. So all I really want to point out here is that the characters are no longer indexed by just partitions, but these primary characters, which are the ones that are relevant, are indexed by a polynomial and a partition. So we get a bunch more characters. But the formula is written in terms of a sign times a symmetric group character, so that's kind of familiar, old news, times a product of some sums of complex numbers. Really, you can think about this stuff over here as just being some complex numbers associated to the eigenvalues of the matrix that we're plugging into this character. So in some sense, this does highlight how the GLNFQ character theory is similar to the symmetric group. It's just got a lot more information going on. And one more thing I wanted to point out is that if some part of mu is not divisible by the degree d of that polynomial f in the index, then the character is 0. And that is basically why, I mean, from the perspective of purely just character theory, that's why that condition, multiplicity of 1 being 1 in mu, is nice. It just simplifies a bunch of the character values to 0, namely. So yeah, anyway, there's not a Wikipedia article that has this formula on it, nor is there a little combinatorial rule for it. Of course, that symmetric group character itself, you can use the Murnaghan-Nakayama rule. Cool. Also want to talk about just briefly some previous results. Oh man, running out of time. Okay. Previous results on characters. I'll just go through a little quickly here. The unipotent characters value on a regular semi-simple cycle type mu element is on the nose a symmetric group character, which is further justification algebraically to me why this definition of cycle type makes sense. Furthermore, if you evaluate an arbitrary GLN of Q irreducible character on a regular elliptic element, you get 0 unless you have an index that looks like a hook shape. And that is analogous to what happens in the symmetric group. If you evaluate a character in the symmetric group on an in cycle and get something non-zero, you have to have had a hook character. So that's another little analogy between the in cycles of the symmetric group and the in cycles of GLN of Q. So altogether, the kind of summary of proving these enumerative results is, well, first of all, that proposition says we only need to care about these primary characters corresponding to hook shapes. The lemma that I wrote down says that we only need to consider values of d, the degree of that polynomial f, that divide every single part of mu, and basically plug in the character values to the Frobenius formula. And then I highlighted this word simplified because actually getting that down to what looks so much like the symmetric group result is the weirdness after that. Basically, having all those extra terms that come from the eigenvalues of the matrices that you're plugging in, just got to deal with them. It's not, none of it's extremely deep mathematics. It's just keeping track of a lot of like Mobius inversion looking at roots of unity. But still, it's still surprising that you can have so many more characters in GLN of Q and boil it down to only the same number of them mattering in terms of the Frobenius formula. And that's what allows you to get the similar looking results. Okay, and then you wind up a formula for just this number, gk mu of q, that I just wanted to print it here to recall that formula. There it is again. Okay, so it's just the number of these k tuples of regular elliptic elements whose product has cycle type mu. And I will point out here also that because this T mu set is a union of conjugacy classes, I don't necessarily know which conjugacy class I'm landing in, nor how often I'm landing in them. We'll come back to that in the open problems section. Okay, next section is on polynomiality. This is the last section before the kind of finale with open problems. And it starts off with kind of a freebie here. If we look back at that main result, it's a polynomial in Q with rational coefficients. So again, that main result is I'm assuming that the multiplicity of 1 in the partition mu is equal to 1 on the nose. And yeah, the reason we get a polynomial is that it starts out as a rational function and it's a counting function. So we get integer numbers infinitely many times. So for example, you could just write down some values. You might start looking at this and say, okay, maybe there's cyclotomic factors except for the Q. Turns out, sadly, here you might think that aside from the Q and the Q minus 1, that everything is Q numbers, like a Q analog of 1, Q analog of 2, Q analog of 3. Unfortunately, not the case. If you look at this other example, you might start to think, okay, maybe the factors are cyclotomic. The examples get big too quickly, but there are examples where you don't have cyclotomic factors, even excluding the Q there. Okay. And what puts that other function, that more complicated function, gkn of q, in a different class is that it is not polynomial. But here's what I was able to come up with. So that much messier looking function, gkn of q, when n is prime, and like I was saying earlier, that's when we should expect it to simplify a lot because this has all these nested sums over divisors of n, so that just reduces how many divisors you have to deal with. It's a quasi-polynomial. So you can find polynomials f0 through fn minus 1. They have the same degree, kn squared, and the same leading coefficient. And that's coming from the fact that they have to all have the same asymptotics. And what property to satisfy is this equation here. If you want to evaluate gkn of prime power q, and it's congruent to I mod n, then you can just plug q into fi. And then one more surprise that simplifies it even more is that f1 is the only odd one out. All the others are equal to each other. So really to specify this gkn of q function when n is prime, all we have to do is specify what f0 is and what f1 is. So for the example with n equals k equals 2, here are those polynomials. And you can realize, okay, there's the leading coefficient. That's the same. The leading coefficient is always going to be 1 over n to the k plus 1. I'm not sure why I didn't include that, but there's the leading coefficient. The degrees you can check are all are the same for the polynomials. Yeah, and here's another example. N equals 2 and k equal, sorry, n equals 3 and k equals 2. We've got these two polynomials. Again, leading coefficient's the same, degree is the same. And then something else that happens when you have a quasi-polynomial is that the generating functions for quasi-polynomials are rational functions. And this is the smallest non-trivial example you can write down, and it still takes 4 lines to squeeze it into LaTeX here. And so the denominator has roots of unity as its roots. The numerator is polynomial x here. And you also notice that I'm letting q range over all non-negative integers, basically because g22 or gkn of q in general has an explicit formula. I don't need q to be a prime power necessarily. But someone pointed out, hey, those coefficients in the numerator are non-negative and unimodal. Right? They go up until 41,830, then they decrease down to 1. So I thought, okay, I might as well plot some of those and see what they look like. So those coefficients that we just saw are, wait, are those? Oh, technically, because I factored this 2 out right here, the y-axis is just kind of cut in half from, or the y-axis is doubled from these numbers. But anyway, these are the same coefficients if you just actually express that whole numerator. So it's, oh, cool, great. It's you're right. It's unimodal. It's they're positive. So then I let k go up to 3. So I increase that up to 3, looking a little more familiar there. K goes to 4. G5 2 of q. Interesting. Then I switched n over to 3 and looked at those examples as well. And they start to look awfully like a normal curve. But I don't actually know why. Yeah, it turns out that it's possible to get various shapes of these coefficients on the numerator of a rational generating function. And just something I kind of came across recently that someone pointed out. So I just haven't really figured that out yet. So that'll be in the open problem session. Or not session, I guess. We're not about to hash some of these out, I don't think, unless you have ideas. But here's some open problems. Here, the first slide of open problem is just some concrete ones to start thinking about. First of all, I believe even if n is composite, that still there's an f1 polynomial that agrees with that gkn of q function on the prime powers congruent to 1 mod n. Just have some data that suggests that, but that, again, that c, that capital C function with that weird integer LCM in the denominator, confusing me. Another one is I would like this q goes to 1 limit of these ratios of probabilities to be true more generally. Unfortunately, when mu is the 1-part partition, because I've got this quasi-polynomial, it's kind of unclear what I should actually do to take a q goes to 1 limit. A little weird, so it's at least not true for that, but maybe it's true for some other large family of values of mu. This is something I also alluded to at some point. I would like to refine this main factorization results to the level of conjugacy classes. Like in Stanley's result, because C mu is a conjugacy class, you can divide by the size of C mu and get factorizations of a fixed element into products of n cycles. But because cycle type in GLN of Q lumps together conjugacy classes, I can't achieve the same effect. Yep. And then, yeah, the open problem that I was just talking about. I don't really know yet why the numerator coefficients look like a bell curve, but they sure seem to. So I'd somehow like to describe them. I've gotten close by taking a large power of like x plus 1 and kind of shifting it around a little bit to get it to line up and scaling it by large numbers, but I'm not close yet to a general description of that. And then the next slide of open problems is the real pipe dreams, long-term goals, which are Q analogs of the following. One, Hurwitz theory. So what topological structures correspond to enumerating factorizations in GLNFQ? On one hand, you can just view GLNFQ as a permutation group embedded in a large enough symmetric group, and the usual kind of Hurwitz theory stuff happens. But I don't find that so satisfactory. I'd love to see some real Q-flavored geometry happening. Another thing is the tree bijection from the introduction. They ask in that paper, the Lewis, Reiner, Stanton paper, for a bijective explanation of the Singer cycle factorization into reflections. So that'd be cool to see. I'm not sure how to do that. Somehow the edges should correspond. Actually, this gets back to that question about reflections being involutions. Because they aren't, it's kind of weird to think about an edge just swapping the two endpoints. The Murnaghan-Nakayama rule, yeah, so I don't have a convenient Wikipedia page description of my character formula lemma. That would be cool to see some more combinatorics going on there. Yep, and last but not least, and I got an interesting email about this recently, the Euclides-Murphy elements are these elements in the symmetric groups and group algebra that have really nice properties and allow you to approach the character theory of the symmetric group in a new way, a different way. And they play nicely with these so-called class symmetric functions. And because GLNFQ's character theory also has a symmetric function description, I'd love to see some kind of analog here. And I've talked with Vic Reiner about this, and I also just got this interesting email about it. It seems like they are at least elusive for GLNFQ if they even exist at all. Something to think about. Okay, well, I think that's it. Thanks so much for being here. Happy to take questions.
Well, let's thank the speaker. Really awesome talk. Clap or add something in the chat or show your reaction. It's a little slower process, but everybody can appreciate the talk. And then let's switch over to questions. So does anybody have any further questions? Lots of good questions in the process.
I had a question. You talked about these generating functions.
Mm-hmm.
Thinking about the numerators, is it even clear that the numerator should have positive coefficients?
It's not immediately clear. No, I mean integers is fine because
yeah.
I mean I guess you could just clear the denominator, but yeah, not sure. Not sure. Great question. It's a weird generating function, and I've played around with some examples. Like, it's definitely not guaranteed that you just kind of pick a random polynomial and get even like unimodal coefficients. Yeah.
Can you say anything about the roots? Like, do they look like they're real rooted polynomials?
Nope.
Okay.
Good question. Yeah, I think Sarah asked me that at some point too. Yeah.
The coefficients a log concave or something? Or?
Oh, I don't know. I haven't looked at that. Yeah. Yeah. It's a mystery to me. A recent mystery. Yeah.
So you're saying that they're not real rooted according to the data you have?
Not real rooted. Yeah.
Okay.
According to what I have. Yeah. They get big. I mean, I've got code. I'm happy to share some code if you want to mess around with them. Let me know.
Yeah. Be interesting to see what the distribution of roots looks like at all.
Mm-hmm. Yeah. Yeah. I'll make a note.
So I'm not sure I understood this condition on M1.
Oh yeah.
My impression was that you, at some point, there was some number that had to divide all the parts of the cycle type, and so if there was a 1 in there, like that simplified things.
Exactly. Yeah. And I'll put
but
a
then what would be the
up
problem? So okay, but what would be the problem then if there were 2 1s?
Exactly. Yeah. I realized through the talk I kind of forgot to address that. So basically, because I'm looking at regular semi-simple elements, maybe I don't need a whiteboard for this actually. Because I'm looking at regular semi-simple elements, I want to make sure that the factors of the characteristic polynomial are distinct. And if there's multiple parts with this multiple, if they're repeated ones, then that's like, I have to consider subsets of the set of degree 1 polynomials, of like distinct degree 1 polynomials. And that didn't allow some of the sums over these of its roots of unity to simplify so much. It's a less, it's much less clear why that multiple ones throws things off.
Okay.
Yeah, and the computation when I had like, when I showed that little sum progress part where I had a cycle type of 2 followed by n-1 ones, there, for whatever reason, I was able to compute that a little more easily in that specific case where I have n-2 repeated copies of 1. I think it was just kind of a coincidence that worked out a little more nicely, but yeah.
All right, so if the questions are coming to a natural end, and we're a little bit over time anyway, maybe now's the time to thank Graham one last time, and then we'll proceed to the rest of the meeting.
Thanks for coming.